In the next few videos, Brian is going to explain the work that got him the Nobel Prize. But before we get onto that, I'd like to explain some of the clues that were around even before 1995 that suggested that something was not quite right with this picture. I'll focus on some of my own work, but there were a number of other people who also had clues that suggested something was a bit wrong with this picture. So, back in 1995, this was a big debate. We knew that space was expanding at the moment, and the question was it following the green line, slowing down quite a lot so it would come back for a big crunch, or was it following a blue line so it would keep expanding forever, but always slowing down? Everybody assumed it had to slow down because, after all, gravity only attracts things, and we knew of no other force. We of course cannot see the future, so what astronomers were looking at was the past. So that's today. And the big debate was which of these lines gave us an accurate picture of the scale factor of the universe versus time. Now, my involvement in this started at a coffee shop in Berkeley, California, when I was sitting with a guy called Bruce Woodgate, and we decided to come to this telescope. This is the Blanco telescope at Cerro Tololo in Chile, and use a new technique and a new instrument to try and look for galaxies further away than anyone had ever seen before. And we succeeded, and we found, actually it turned out to be two colliding galaxies, these two little red dots down here. They're called Blob 1, and they were, at the time, one of the most distant pairs of galaxies ever discovered, at a whopping 10.8 billion light years, a redshift of 2.38, staggeringly distant. But the puzzle was, as you can see, this is a Hubble Space Telescope image, these two galaxies are actually quite red in colour. Now, how do you get a red-coloured galaxy? Well, galaxies are just collections of stars. And generally speaking, you get some blue stars, some yellow stars, and some red stars, and every colour in between, of course. If a galaxy has just been born, it will have all these types of stars. It won't have very many blue stars. These are the blue giants, the very massive stars, but they're extremely bright. It'll have rather more yellow dwarf stars like our Sun, a bit fainter, and tons of pathetic red dwarf stars. Even though they outnumber everything else, they're so faint they don't add up to much light. So we'll get a spectrum that looks something like this. So remember, here's wavelength, and here's the energy per unit wavelength, the flux per unit wavelength. The blue stars have a spectrum like this, so it peaks down here at short wavelengths, whereas the yellow stars peak at yellow wavelengths, and the red stars peak out at red wavelengths, strangely enough. And if you add up these three spectra, you get the purple line, which peaks in the blue and the yellow thereabouts. And so, if a galaxy is very young, that's the colour you expect it to be, a somewhat bluey-yellowy colour. Galaxies which could keep on forming stars, like our own Milky Way, will maintain this colour because they're always forming new blue stars. But some galaxies, elliptical galaxies, they seem to form all their stars in one burst right at the beginning. So you form a huge number of stars very early on, and then no more stars are formed. In this case, the blue stars, the massive ones, don't last very long. They burn furiously, but they die young. So after a few 100 million years or so, they've gone. No new ones are taking their place because no new stars are forming. So now we only have the yellow and the red stars. So we've got the yellow star spectrum and the red star spectrum. Add them together, you get this new purple line, which is looking much more yellowy red. And if this galaxy keeps going for even longer, eventually the yellow stars will disappear. A star like our Sun lasts about 10 billion years. After 10 billion years, it's gone, and all we're left with is the red dwarf stars. At this point, the galaxy will look extremely red. It'll have a red dwarf colour. So this is why galaxies can become red. What did our data show? Well, here are the data points. Here is the young galaxy spectrum, the middle-aged galaxy spectrum, and an old one. And you can see that this galaxy appeared to be middle-aged. Those data points fit the model there most precisely. So this is puzzling. We're looking back 10.8 billion light years. So we're looking at the galaxy not as it is now, but as it was 10.8 billion years ago. And it's already middle-aged. So, why is that a puzzle? Why couldn't a galaxy be middle-aged that far back? Well, let's look at these models. We're looking at the scale factor of the universe against time. Here is present day, A of t equals 1. These galaxies, blob 1 is at a redshift of 2.38. So if you remember, the scale factor is equal to 1 over 1 plus the redshifts. So it's 1 over 3.38. So we know that somewhere down here is the galaxy when we saw it. So let's say the blue line was correct. The universe is going to expand, it's slowing down, but will always keep going. In that case, we see the galaxy at this time here. However, we know from looking at the red colours that it must be old enough to have got rid of the blue giant stars. This actually gave an age of about 700 million years, which means that if we see the galaxy here, it must have formed here, that being 700 million years. Which means it formed here, but you see, for the blue line, the scale factor is 0 there. That means the universe is no size there. That's when the Big Bang was. So what this means is this galaxy is forming maybe about 500 million years before the Big Bang. Oops, that sounds difficult. Well, how about we try the green line? So a universe that's going to expand and then collapse back together again. Same thing applies. The galaxy is at redshift 2.38, so it must be here. If it formed 700 million years earlier, it formed there. And once again, this is before the Big Bang for this cosmology. So either of the two sensible models, models in which the universe slows down, we end up with the embarrassing feature that this galaxy is older than the universe. We can get away from this a bit if we assume that in fact there was no mass in the universe, it was just expanding at a steady rate. If we have it here, it forms there, which is actually after the Big Bang. So that's good, but it's not very far. You're actually talking about a pretty massive galaxy. This galaxy weighs about 10 to the 11 times the mass of the Sun, forming in quite a short time after the Big Bang. What you'd really want is a universe that did something like this, curved the other way. In that case, it would be here, formed there, and so it was formed a long time after the universe started. That would be ridiculous, though. A universe that curved that way, why, that universe would have to be speeding up. There'd have to be some repulsor force. That was clearly stupid, so no one believed it. And there were good reasons not to back then. My galaxy wasn't the only one that showed these features. Quite a few galaxies and stars were showing up that appeared to be older than the universe. But these measurements are very hard. For example, the red colours of this galaxy, maybe it's caused by interstellar dust rather than by an old stellar population. And it's really hard to measure. Very often we would observe for many, many hours and only collect like 5 or 10 photons from this thing. This thing is very, very faint, as you'd imagine, being at the far end of the universe. So people weren't quite sure of it. But nonetheless, people keep finding these things that appeared to be older than the universe, which was worrying. Thankfully, Brian came along to tell us a proper explanation for this.